quite complicated, sophisticated looking dynamics of an action potential. We're going to show how we can, what we're kind of going to do is show how that's possible through calculating the phase. So, sketching the phase. So, let's kind of now move on to that part. Okay, so, this is really going to then be another revision of sketching phase planes. So, just as kind of a word of point here, actually, this is a character of a model. So these V's and W's, I kind of talk to them as kind of voltage and concentrations of ions. They're not really quite that. They're just trying to characterize this complex Hodgkin and Huxley sort of model in a kind of a slightly sort of simpler setting. So V and W don't really quite correspond to normal biological variables. And actually, as a consequence of that, is that actually, unlike most biological models, where we would want our variables to be non-negative, because we're normally talking about things like animal populations, cell densities, chemical concentrations, so it doesn't make sense to consider those when they're negative. In this case here, these are kind of more, slightly less sort of specific variables, and actually they can also take negative values for these V and W. So we are going to kind of need to kind of consider this slightly wider phase plane when we're kind of doing the sketching. Okay, so we're going to plot the phase plane for V and W. First steps to that are kind of plotting the null-clines. We've actually already done that in the previous sort of step. We've got V null-cline, and the V null-cline basically has this shape of kind of a cubic. So has this shape here. That's my V null-cline, and this is the line along which V dot is equal to 0. Okay, so that's kind of that's the V null-cline. Well, kind of why is plotting the null-cline important for understanding the form of solutions in the phase plane? Well, basically what it does is because it divides this phase plane into different regions. You know, we're dealing with kind of nice continuous functions in these sort of equations. This is the line along which V dot is equal to 0. So above that line, we'll either have V dot positive or V dot negative, and below that line, it will be the other way around. So the point of those null-clines is they kind of nicely partition the phase plane space into the regions where, in this case, V dot is greater or less than 0. And how can you kind of then do that? Well, people kind of have different techniques to kind of do that. You kind of almost develop your own one. Kind of my kind of way of kind of approaching this is, as I say, we've got this line along which V dot is equal to 0. We now want to find out where V dot is positive and where it's negative. So the best way to kind of do that is just kind of take a point somewhere up in this region that we know is above the null-cline. And kind of an obvious point would be up here on the positive W axis. We know that's clearly above this null-cline. Take a kind of an arbitrary point along there and just plug it into this equation for dV by dt. So dV by dt is V1 minus V, V minus A minus W. If we're on this kind of positive vertical axis, V is clearly 0, so that term just disappears. W is something positive, so hence dV by dt has got to be negative. And that tells us that generally above that null-cline, because we've got continuity here, we've got V dot less than 0. And I could have used exactly the same argument to kind of deduce that below that null-cline, V dot is positive. You know, for example, I could take a point down here on the negative axis here, where W is less than 0 and V is equal to 0. Again, that first term is going to be 0. W is negative, so we'd have dV by dt as positive in that region. Okay. So, as I people have different ways to kind of use this sort of information. As I say, I find the easiest way is to say, once you've drawn those phase planes, that allows you to kind of identify some point that you know is one side of that curve, and then kind of just substitute in and make it kind of the appropriate reduction. Okay, so that's kind of what I've got from that kind of V null cline. Let's now kind of do the same with the W null cline. So our W null cline is simply straight line. So simply this straight line here. This is the line along which W dot is equal to 0. Of course, as I said, the gradient of that straight line will depend on the parameters B and gamma, and of course I could have drawn it so it intersects this at several points, but that's actually not the case that's relevant to the action potentials. We're not looking at that specific case. But again, I can kind of do exactly the same sort of thing. Once I've got my W null cline, this is where W dot is equal to 0. So above that null cline, we must have W dot either greater or less than 0, and below that line, the other way around. So in this case here, well, we can do the same sort of argument. I could take a point here on the positive W axis, V is equal to 0, W is something positive, so hence from that equation for W, we're going to have W dot less than 0 above the line and W dot less than 0 below the line. Okay, so that's kind of the key, probably the key step when you're kind of doing these phase planes, is using this information from the null cline to deduce the regions where V and W are increasing and decreasing.
Is it the wrong side?
Oh, sorry, that should be greater than 0 down there. Yeah. That's the area, yeah. Okay. Okay. So now we've got this sort of we've got this kind of information. Should also probably mark this steady state down here at 0, 0 as well. That's the steady state. Because it's the intersection of those two numbers. Okay, so we kind of doing well. We can now start to kind of piece together all of this information and get some trajectories. Well, try and be as careful as possible when you're kind of sketching trajectories. What do we kind of know? We know our null clines. Well, the null clines, this V null cline is the line along which V dot is equal to 0. So anywhere along this line, V is neither increasing or decreasing. V is along the horizontal axis there. So if V is neither increasing or decreasing, any trajectory should pass through this line kind of vertically. So I can kind of indicate those kind of little vertical lines there, just to be careful that when I kind of sketch my trajectories, that I've got to pass through this vertically. The W null cline is where W dot is equal to 0. Along the W null cline, W is neither increasing or decreasing, so I've got to pass through that horizontally. Okay, so that's kind of just always a kind of a worthwhile step. Now let's kind of work out the direction of the trajectories in the different sort of regions. And basically, what we've done with the kind of the null clines is divided our phase plane into 4 regions. This region down here, this region kind of in here, this region up here, and this region over there. And we now want to, as I say, kind of work out how V and W are changing in those different regions. Let's first look down here. So in this region, we're below both the W null cline and we're below the V null cline. So V dot is greater than 0. We're also below the W null cline. So we also have W dot greater than 0. So we're increasing with respect to V, so we're going to be moving towards the right with respect to V. We're increasing with respect to W, so we're going to move upwards to indicate that kind of this region here, my trajectories are going to be pointing up and to the right. So in this direction here. Okay, so that's kind of this first area. Let's now kind of look at this in-between space between this line and this line up here, so this kind of area here. Well, what have we got here? We're above the V null line, so V dot is negative, and we're below the W null line, so W dot is positive. V dot is negative, means we're going to be moving towards the left, because V is my horizontal axis. W dot is positive, so we're going to be moving up in this direction here. So, in this region, my trajectory is going to be moving up and to the left. Okay, so that's kind of that sort of region. This region here, we're now above the W null line, so W dot is negative. We're also above the V null line, so kind of furnish that. V dot is negative as well. So we're decreasing with respect to both W and V, so trajectories are going to be moving down and to the left. And this final region here, this one over here, well, what have we got here? We're above the W null line, so W dot is negative. We're now below the V null line, so V dot is positive, and hence we're going to be increasing with respect to V, so moving towards the right, decreasing with respect to W, so moving down, kind of trajectories will be pointing down and to the right in this region. Okay, so we just kind of use all of that kind of information on where V and W are increasing, decreasing, etc., and we can work out things accordingly. Okay, so now let's kind of think then two typical trajectories. Well, to kind of show the dynamics of the system, I'm going to consider two very specific starting points. Let's kind of first take a point that's somewhere down here on the V-axis, so somewhere down here. And I'll kind of label this as position 1. So what's going to happen to trajectories down here? Well, we're kind of in this in-between space. We're in this region where V dot is negative and W dot is positive. So my trajectories are going to be moving initially in this direction. And they carry on moving up and to the left until they hit the W null line. And of course they have to cross that horizontally. So the curve roughly is going to look something like that. We're now in the region where we're moving down and to the left. So we're going to be moving down to this. We know that this steady state 0 is a stable steady state. So when we get sufficiently close to it, trajectories are going to be drawn into it. It's going to pull the trajectories in. So, well, I may kind of slightly overshoot. I may not, but I expect a typical trajectory to look something like that. Okay, so that's kind of from that region here. Let's now kind of move things to the other side of here. So, call it some point 2. So we've just flipped over to the other side of the V null line. Well, now we're going to move up to the right. So the trajectory takes a very different sort of direction initially. It's going to move up in this direction. It's going to cross this V null line vertically, so it's got to kind of bend up and kind of cross that vertically. We're now in the region where we're moving up to the left, so we're going to go in this direction here. We cross this one horizontally. We now kind of come down and, well, may just cross into that sort of region here. And eventually we get back to this stable, steady state at naught. Okay. So, information on the directions of the trajectories to kind of reveal these sort of different potential solutions that we could get for this system. And how does this translate then to that picture of the action potential I showed earlier? Well, trajectories, first, the path of the trajectories to your phase plane is effectively giving you an indication of how the solutions are changing according to your, well, in this case, time, my independent variable. So we can use this and then kind of work out what's happening to the voltage, well, V of t, I'm going to say it's not strictly the voltage, but it's kind of serving to describe the voltage, this V of t. We can use this to kind of see what's happening to V over time. How do we do that? Well, let's kind of look at these two different initial conditions. So probably should have, to be accurate on this phase plane, I should have kind of labelled these points as 0, A, and 1. So that's where that kind of V null plane is intersecting the axis at these parameters. Okay, so let's see kind of what's happening here. So got this parameter A here that is describing this kind of intersection here, and in this case I was starting with an initial condition where V was just a little bit below 1 here. W was equal to 0, V is less than 1. In this case, we just move immediately, as we kind of move along the trajectory, we're decreasing with respect to V. This is just going to describe a case where basically starting from this point here, V decreases and V drops down to 0 over time. That doesn't look like my action potential at all. So we just simply drop down to 0. But what about this point 2? We've moved to the other side of this null plane, and rather than V initially increasing, V starts to increase. So we're moving to the right with respect to V, and we carry on increasing until our trajectory hits this V null plane. So the dynamics here look a lot different. They immediately rise up. They get to the maximum up here. Then they start to decrease. So then they start to decrease. Because we've taken this extended sort of detour in the phase space, it kind of slightly overshoots down there. So it kind of carries on decreasing, kind of overshoots and gets into kind of the negative V region. But eventually, we again cross that V null plane. So eventually, we kind of get down to a minimum before, again, it returns to 0. So, two different trajectories showed two very different dynamics. Along the V-axis, no, because actually, if you think about it, we're actually in the region where, so there's not a V null plane along the V-axis. Okay, so we're actually in this kind of region where we start where V dot is strictly less than 0 and W dot is strictly positive. So we kind of have to move immediately off the axis. Okay, so got these two different trajectories here, and the second one here kind of nicely describes the shape of this action potential. Now, kind of more importantly, this is an example of a specific sort of property. So this is an example of an excitable system. And what I mean by that is what we're kind of showed in this sort of through this kind of sketch here, that by just kind of changing things a very, very small amount, we get a completely different type of behaviour in this sort of system. When we start to the left of this axis, we decrease down. When we start to the right of this axis, we shift upwards and then come down after. So this change, this kind of critical change according to this parameter A, describes this idea of excitability, a big shift in behaviour. And think about what this kind of means from a kind of a biological perspective. What this is kind of saying is that in order to ignite this action potential, you need enough of a shift into the system. As I say, our kind of resting state is 0, 0. That's kind of our kind of nerve without kind of anything sort of going on. That's at 0, 0. If you shift a small amount, perturb a small away from that steady state, then you get this sort of dynamics. You just very quickly return back to the resting state. However, if you give it enough of a push, you take this extended route through the phase plane and initiate this action potential. Can anybody think why that would be an important property for the nervous system? Yeah, exactly. It's accounting for the fact that we've got noise going on all the time in the system. Yeah. If we've got even a very tiny perturbation from the steady state, we've kind of ignited this big action potential, and even just the tiniest fluctuation due to noise would kind of send a signal going along my action potential and send a signal going around the body. We don't want that sort of property. That would be not a robust system. We'd be, stimulated constantly, basically, if we've got signals going around all of the time. The point is, you need this kind of threshold of excitability. You need enough of a push to ignite this sort of wave going along it. So you need enough of a stimulus to ignite that. So it's an example of an excitable system where you have this threshold response. And excitable systems happen in a lot of biological systems. They're also fundamental for the beating of our heart. The reason our kind of heart beats in coordinated fashions is because it's a muscle. All of the cells are basically told to contract at the same time. And they do that through a coordinated wave that passes through the heart, contracts those cells, and creates a coordinated heartbeat. If they were all contracting in a kind of almost sort of as and when they want, we would clearly have kind of a very dangerous situation. The heart would not be able to beat in any sort of controls. Okay, so that's just that kind of just finishes off then this example of chapter 1. And as I say, partly a kind of a revision of this kind of sketching of the phase planes, but also kind of indicating this kind of importance of excitability in the context of neural signals. But we're now going to kind of finish off today's lecture by kind of moving on to the start of the next section of the notes, and this is mathematical biochemistry. Okay, so mathematical biochemistry, on the face of it, may not sound kind of very interesting. The name biochemistry is often a turn off for a lot of sort of people. But why is it important, and why is it important to do mathematical modelling of biochemical systems? Well, very simply, because everything that our body does comes down to biochemistry. All of the cells in our body are basically little boxes of chemical reactions. You've got proteins interacting with other proteins, and that's coordinating the behavior of the cell. That's telling them when to divide. That's telling them when to do other key things. to behave abnormally, and that can be, for example, when cancers sort of grow. So, you know, understanding mathematical biochemistry is absolutely fundamental for understanding how cells are behaving and what's happening when things go wrong. This is not a very good figure, you won't be able to see this. Another key important aspect of biochemistry in our body is, of course, just the basic process of how our body converts sugars into energy. That's what's called the glycolysis pathway, and the glycolysis pathway is basically a set of chemical reactions that steadily kind of go through a set of processes converting glycolysis into end sort of products, and along that step they release energy, and that energy is then critical for the cell functioning and the body function. Other examples of biochemical events in our body are things like the coordination of hormones. So we've got various hormones that are regulating various aspects of the body. They, in a lot of cases, have specific cycles associated with them. That's fundamentally a biochemical signaling processes. And of course, when it kind of comes to, in terms to sort of treatment of disease, then of course, if you apply some sort of drug to the system, you're potentially changing all of these sort of processes, and you therefore kind of want to understand how these drugs are impacting on the body. So it's very important to kind of study this kind of process of biochemistry. We've got this in the kind of the main course notes. There's a kind of an introduction section in your kind of main course notes that basically just sort of says about these kind of key points of mathematical biochemistry. So for example, conversion of sugar into energy, cell function and behavior, hormone production, action of drugs. And that's a kind of a list of 4, but I could really kind of carry on, etc., 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 etc. It's really absolutely critical to our body's function. We're really just a big collection pieced together of little boxes of chemical reactions. So we'd obviously therefore like to have a framework for modelling these sort of processes. So how do we come up with mathematical models to describe chemical reactions? And that's where the law of mass action comes in. And the law of mass action, as I say, basically gives you a pathway for a given chemical reaction to write down a set of differential equation models to describe the rates of the chemicals involved. So, I'm going to look at this law of mass action, and I'm going to introduce some kind of notation here. So I'm going to use uppercase to represent individual molecules or chemicals. So, for example, if I kind of put an uppercase, I could be referring to a molecule of hydrogen or something like that. It's just to describe a specific sort of molecule or chemical. And then I'm going to use lowercase to represent the corresponding concentration. So, reactions are, of course, the result of individual molecules binding, joining together with other molecules and converting that into something else. But of course, typically in a lot of situations, we've got huge numbers of those individual molecules involved at any one time. We don't necessarily want to model every single individual one. We want to more track how the concentration of some substance is changing over time. So while we're going to state our kind of basic chemical reactions using this uppercase, we're going to then write down rate equations in terms of the concentrations. Okay, so that's going to be kind of a key notation. And a chemical reaction is typically written in the form something like the following. You basically kind of looks a little bit like kind of an equation. You have something on the left-hand side, which will be the reactants. So in this case, we've got two reactants, a molecule of type A that joins together with a molecule of type B. These react together, and you indicate that with an arrow, and that creates some product C. And this is the way we write a typical reaction where a molecule of A combines with a molecule of B to form molecule C. So, i.e. molecules A and B combine, react to form C. Now that reaction usually, in fact it always has a rate of reaction, a rate constant to kind of indicate this rate of reaction, and you often kind of also then see some little symbol above this, some sort of K, which is a rate constant, which is basically saying how fast this reaction can take place. So K is the rate constant. So, given that we've got this as a kind of reaction, how do we kind of convert this into differential equation form? Well, this is where we use the law of mass action, and the law of mass action states the rate of reaction is equal to the rate constant times the product of the concentrations of the reactants. Okay. So, the law of mass action is basically a way of kind of taking this kind of information and then kind of converting this down into a general rate of reaction. Very simply, it says that that rate of reaction is the rate constant times the product of the concentration of the reactants. And this law of mass action, it works well if you're dealing with large numbers of molecules. If you've got lots of molecules of A, lots of molecules of B. It doesn't work very well when those numbers of molecules go down to very small numbers, and that's when we need to use stochastic modeling techniques to kind of describe those situations. If you've got large numbers of molecules, it provides a good approximation for this process. So, in the context of this reaction above, so for the above, what's the rate of reaction? Well, say it's the rate constant, and that's indicated by this K, and it's the product of the concentration of the reactants. In this case, we've got two reactants, A and B. We're talking about the concentration, so we kind of talk about them, you kind of refer to those using the lowercase. It's simply going to be K times the concentration of A times the concentration of B. And once we've kind of got that information, we can then directly write down our differential equations for this So the A by dt, B by dt, and the C by dt. And what do you have to do there? Well, really, once we've got this information of the reaction, it's just then kind of seeing whether or not substances are being used up or produced as a result of this reaction. A is one of the reactants, so it's going to be destroyed when you create this molecule C. So the A by dt is going to be minus K times AB. Similarly for B, B is being used up, so it's going to be minus K times A times B. C is being created as a result of this reaction. It's going to be created at this rate of reaction, so we'll have plus KAB. Okay. So the law of mass action, as I say, kind of gives us this kind of toolkit for writing down differential equation models. But how can we extend this concept? The reaction I kind of gave up above here is an example of a one-way reaction. So A and B form C, but there's kind of no backward route in that. Once C has been created, it's locked in there. Well, that often doesn't happen. Typically, you have reversible reactions. The reactions can go in two ways. The reversible reactions extend this notation above here. Rather than having a kind of a one-way arrow, we now have a two-way arrow. So A plus B, and then this kind of two-way arrow to form molecule C. And this reaction can take place in both ways, so there'll be a different rate constant with the forward and the backward process. So the forward rate constant could be K1, and the backward reaction may have rate constant K2. So, how do we kind of then write down our differential equation model for this case? Well, we've effectively got two reactions going on. The forward reaction is the same one as before. A plus B forms C, and the rate of the reaction is K1 times A times B. The backward reaction, in this case, this is going from C to A and B. So my reactants in the backward reaction is this C. It's just this molecule C, basically. That's, so in that backward reaction, we're going to be taking place at a rate. The rate constant for that backward reaction is K2, and we've just got a single reactant involved in the backward reaction. It's C. Okay, so those are kind of the rates of our forward and backward reactions. Now we can write down our differential equation model. And now again, we kind of have to think whether or not things are being created or destroyed. In the forward reaction, we lose a molecule of A, because A combines with B to form molecule C. So we're going to have this minus K1AB to indicate that we're losing A in that backward reaction, in the forward reaction. In the backward reaction, C is creating a molecule of A. So we create a molecule of A, we create it at this rate of the backward reaction, so we'll have a plus K2C. Then you can do things for the other equations similarly. B by dt. B is going to have exactly the same sort of dynamics as A. It's being lost in the forward reaction, but it's being created in the backward reaction. So dB by dt will be minus K1AB plus K2C. And for C, the signs are going to be flipped round the other way. We gain a molecule of C in the forward reaction, we lose a molecule of C in the backward reaction. We'll have plus K1AB and then minus K2C. So those are kind of the first two simpler cases. Well, I'm going to leave this now as kind of an exercise between now and kind of the class sort of next week. Let's kind of B form A plus B plus 2C. Okay. So we've got a reversible reaction. This is one that can take place in two different directions. The forward reaction, we start with 2 molecules of A now and 1 molecule of B. So the reactants in this case are the 2 molecules of A and the single molecule of B. The backward reaction has molecules A, B and 2 molecules of C, and that can go, so in that case, for the backward reaction, the reactants will be A, B and 2 molecules of C. And between now and next Tuesday's sort of lecture, we're going over as a challenge, see if you can kind of think about how this kind of law of mass action would apply to this sort of case. And then we're going to go through a couple of further examples on this.
When you have to wait, the is going to be twice. Okay, keep it. Q1.